Huang is going to be telling about integral measure equivalence versus quasi-isometry for some right angle.
Okay, thank you very much for the introduction, and thank the organizer for inviting me. It's a great pleasure to be back in Montreal. I used to be a postdoc here, and I love this city. Okay, so today I want to talk about the relation between measure equivalence and quasi-isometry. So maybe to motivate, so I'm going to spend the first half an hour just to give you some motivation and do some overview. So okay, so okay, so is everything good?
Just need to mute you there. Okay.
Okay, there's still this thing in the middle. Okay, great. Okay, so first I want to let me see if this one is working. It seems this one is not, the clicker is not working. So
Point at
I should point over here. Okay, great. Okay, so I want to maybe start with the definition of quasi-isometry, but probably not the usual definition you see. So this is actually the definition given by the Gromov. The two finite generated groups are quasi-symmetric if we can find commuting a proper discontinuous action of G and H on the same locally compact space, such that the action of each factor is co-compact. Okay, so this may be a little bit different from the usual definition you see, but I wanted to first to say that this is really a good definition and it's very inspiring. So I want to explain. Suppose we already know G and H, two finite generated group, are quasi-symmetry. Then how do we get this definition? Okay, so basically we're going to take this X to be the set of all ALA quasi-symmetry from G to H. So this is a set of maps. Okay, so notice that this set is non-empty if I already know G and H are quasi-symmetric. So that means for some choice of L and A, the set is going to be non-empty. Okay, and then okay, so now let's see what are the requirements. Okay, so now I want commuting action. So I want G acting on this set and H acting on that set, which is commute. So I can let G acting by pre-compose and H acting by post-compose. Okay, so G acting left translation, pre-compose, and left. So that's how I have G and H acting on this set, which is which commutes. And okay, so now I need this set to be like a locally compact topological space. What do I do? So I just define the most naive topology on this set. It's a topology of pointwise convergence. And it's not hard to show this is actually a locally compact topological space. And then so now you see I think the rest is not hard to verify, so we need to check proper discontinuous and co-compact. Okay, so this is how you go from one definition, the usual definition, to this a little bit strange definition. Okay, so what is the point of this definition? So somehow it's sort of a dynamical way of thinking about quasi-symmetry without referring to the matrix on this group G and H. Okay, so wait, so where should I point?
Should be working.
Yeah.
Just to check, so X, maybe you just said it. The point is that X in this is not a matrix space.
Yeah, X is, yeah, that's perfect. So that's a perfect question. So I should clarify, X is not a matrix space. Here the action is set just by homeomorphism. So there's no metric in this definition. That's one of the interesting point of this definition. Okay.
So the actions are by homeomorphism?
Yeah, action by homeomorphism. Yeah, thank you.
What is commute?
Commute means that means that I have G times H acting on the space. So any homeomorphism come from G action and any homeomorphism come from H action, they commute. No, it's some action. There exists a space and there's some action of G and some action of H commutes. Okay. So it means that it means that I had an action of G times H acting on A on the space. So that's maybe that's the faster way of saying what does commute mean. Maybe I can just use my keyboard or yeah. Okay, it's great that we have chance to clarify this definition. So because this is actually very important. So any other questions for this definition? I can spend 5 minutes. So, is the definition clear? Yeah, question are welcome. Okay. Okay, so this may be a strange definition, but I want to say this is actually fun to think about quasi-isometry in this way. So it's like okay, so now from this okay, so it comes out. Okay, so from this definition, okay, so I'm just going to extract part of this definition. We define a topological coupling between two groups, let's say G and H, to be an action of G times H. Okay, so maybe this is a better way of saying two action commute. Okay, so to be an action of G times H on a local compact space of homeomorphisms, set the action of each factor, that means the action of G and action of H is proper discontinuous and co-compact. I'm just repeating the definition, okay? And then, so now notice that here we're doing everything in the topological category. So you could, it was actually the idea of Gromov is trying to maybe change the topological category on other category you like. You can think about a set theoretical notion or even measure theoretical notion. Okay, so that's what going to lead to the next definition. So, okay, so basically we can just trying to translate it, this definition, replace topological space by measure spaces, and then trying to do the most natural thing you would like to do. So we define a measure equivalence coupling between two countable groups. So notice that here I'm just switch from finite generated group to countable group. Okay, so the countable group don't have to be finite generated. Okay, so we say that it's basically okay, so a measure equivalence coupling is basically we had a commuting action, basically G times H on some measure space. Okay, so now instead of acting by homeomorphisms, I want action to preserve the measures. Okay, so now instead of action, I want the action to be proper discontinuous. Here I want the action of each factor to be free. Okay. And then instead of want the action to be co-compact in the topological case, I just want the action to have finite measure fundamental domain. So this would be the most naive thing with trying to write down if you're trying to just do a measure theoretical version of that. Okay, and then okay, so now this would be one definition. You could ask, okay, why measure space? So you could also consider other categories. So okay, it seems at the moment these are the only two things I can say something about. So I won't talk about other sort of variations. Okay, so okay, so now, and we're going to give this definition to countable group G and H are measure equivalence if there's a measure equivalence coupling between them. Okay, so now you may be wondering, okay, maybe I'm giving the talk in a World Conference because there's actually a measure group theory conference also in this CRM program. But today my goal is to try to convince you that I'm actually not going give the talk in the World Conference. This conference really belongs to cube complex. So there will be a lot of, so I'm going to study measure equivalence, but basically via tactics of cube complex and combinatorial geometry. Okay, I'm not in the World Conference. So okay, so now I need some examples. So the simplest example to think about is okay, so I'm going to take lambda to be a Lie group, or more generally some locally compact topological group. And then so we take two lattices in lambda. So lattice means a discrete subgroup with finite co-volume with respect to the Haar measure. Okay, so and then so now I want to claim that these two lattices are actually measure equivalent. So the way to do is that, okay, so now I need to show that there's a measure equivalence coupling between two lattices. So okay, so now what I need to do is I need to have a commuting action of these two lattices on some measure space, right? So the natural measure space I'm going to choose is going to be this ambient Lie group with the Haar measure. And then the two action, I want these two action to be commute. So I just take one left translation, one right translation. They're going to commute. And then the action is clearly free. And the action has finite measure fundamental domain because I debound this discrete subgroup finite co-volume with respect to Haar measure. Okay, so that's one example. That's sort of main example you just to have in mind for measure equivalence. So notice that here the lattice don't have to be co-compact. They okay. So now, okay, so also another comment is that if I take two co-compact lattices, co-compact lattice means that the group mod out the subgroup is compact. Okay, so and then if I have two co-compact lattice, then you can it's not hard to show that to see that this lambda is both a topological coupling and a measure equivalence coupling between these two lattices. Okay, so now in this case we know two cocompactors. They're both ME and QI, so metric equivalence and quasi-isometry. Okay, so now this is actually, I think this is this example is actually sort of one motivation behind this definition. So it's like I have this notion of, let's say I see two groups sitting inside the same ambient new group nicely, and then so if I try to the ambient new group has a group theoretical structure and has some topological structure and have some measure theoretical structure. I can try to forget some of the structure. If I forgot group theoretical structure, and for example, forgot about topological structure, I can just go to the metric equivalence. Okay.
Can I ask a follow-up question?
Yeah.
Sorry, I'm so confused.
Oh, sorry.
Okay. Let's look at at this example, and I'm going to be very, very basic, right? My lead group is PSL2R, which is like the simplest thing we could possibly think of, right? So I have two different co-compact lattices,
right?
Two different
Subgroup,
groups,
right?
With very different hyperbolic structures. I don't see why like the action of G followed by the action of H on the hyperbolic plane can be the same as the action of H followed by.
So the way I think about it is, okay, so let's just think about the group. I have the same group. I have two subgroups, and the first subgroup acted by left translation, and the second subgroup acted by right translation. Okay. So that's to make them commute. Okay. So more questions? Okay, so good. Okay, so now so there's one simple thing I want to mention. So it's like so this is something we expect. So if I pass to a finite index subgroup or quotient by a finite normal subgroup, that's still QI, but the same thing holds for ME. Okay. So now the next question is, okay, so we see the definition of ME and QI, they're sort of similar. So it's natural to ask whether they're actually related to each other. So the bad news is that in general they don't speak to each other. So this is okay. So this is the example already mentioned by Dave. So we take the PSL to R. Okay, so the isometric group of the hyperbolic plane, and then I can take two different lattices. One is the genus 2 closed surface subgroup. Another we can take like a non-uniform lattice where the quotient is not compact but still has finite volume. I take the free group. Okay, and then we know by definition they are measure equivalent, but they are not quasi-isometric because they have different boundaries. Okay. Another thing is that so there's like this measure equivalence turns out to be sort of useless to study amenable group because all infinite countable amenable group are measure equivalent to each other. In particular, Z is measure equivalent to Z2, but clearly these two groups are not quasi-isometric. Okay, so from here, if you look at amenable group, then that motivates you to throw out the idea that we should do something about the relation between these two concepts. Okay. But and also I want to see there's other examples of group which are QI but not ME. The simplest example actually come from some right-angle Artin group. So this right-angle Artin group, they are all quasi-isometric to each other, but they're not measure equivalent. It's measure equivalent to each other because considerations come from L2 Betty number. Okay, so this basically shows that in general we should not expect any relation between them. Okay. So, but I want to say that if you add some more conditions, there are actually interesting relation between them. Okay, so now I want to also mention some rigidity results. So that's sort of a sharp contrast to my previous slides. Okay, so the first everyone's favorite place to prove rigidity is high rank lattice. So there is both ME rigidity result and QI rigidity result, and they basically the same statement. So I take a high rank simple lattice, and then I take a simple Lie group and take a lattice. So just ignore the irreducible. Okay, so here, so then in the QI side, it's known that any finite geometric group H quasi-isometric to this high rank lattice is actually virtually a lattice in the same group, same Lie group. Okay, so this is the statement in the QI side. So, and then there's a similar statement on the measure equivalence side. So any countable group measure equivalence to G is virtually a lattice in G prime. So if you're not familiar with high rank simple Lie group, just think about SLNR and SLNZ, where n is bigger than 3. Then this says that any any group we can imagine, which is either Qi or ME to SLNZ, has to be a lattice inside SLNR. Okay, so maybe up to quotient by normal, finite normal subgroup, or passing to a finite index subgroup. Okay, so this is what the very strong rigidity result we see in the high rank lattice, and there's also theorems for mapping class group. This is another place where people like to find rigidity. So in the Qi side, there's outside a few sporadic cases, any finite geometry group Qi to a mapping class group is virtually G. So virtually means that the isomorphic up to passing to finite index subgroup or quotient finite normal subgroup. Okay, so and the similar exactly same statement holds for measure equivalence. So there's a strong rigidity for group measure equivalent to mapping class group. So now I want to make a remark on, you see here I see two different forms of rigidity. The rigidity in mapping class group is that what I know is that any group ME or Qi to this group is virtually isomorphic. Okay, so that's a very strong form of rigidity, and that form is actually not true for this high rank lattices. Okay, so for high rank lattices, you could have groups which are Qi or ME to this group, but they're not virtually isomorphic. But it's like a slightly weaker it's a slightly weaker form of rigidity that if you take the collection of all the, for example, let's think about SLNZ. If take the collection of all groups which are Qi to SLNZ or ME to SLNZ, they can be sitting inside the same ambient Lie group as NR. So it's like the collection, the class of all groups is uniformized by the same locally compact group. Okay, so that's sort of the first type of rigidity. Okay, so now I want to sort of formalize this. So okay, so what I'm going to say that because sometimes when people saying something is Qi rigid, ME rigid, they mean different things. Okay, so maybe I just make a definition just for the sake of this talk. Okay, so because I think other people has different form of rigidity. So there are many different form of Qi rigidity or ME rigidity. Okay, I'm going to say a finite geometry group is Qi rigid. If I just look at the class of all group Qi to quasi-isometric to this group, then they sit inside the same locally compact topological group. So that's sort of like what happened in the high rank lattice. Okay, so that's a uniformizing object. Okay, and then okay, so here I want to emphasize virtually means okay up to passing to finite index subgroup or quotient by finite normal sub. Okay, so virtually, so we always allow that. And then there's a stronger version is that any other finite. I'm going to say strongly Qi rigid if any other finite generated group Qi to G is actually virtually isomorphic G. Okay, and similarly we define the same thing in the ME side. Okay, rigidity and strongly ME rigid. Yes. For example, if you just apply this definition to G, then
Just said other finite.
oh yeah, you're right. Yeah, so you should say okay. So maybe delete other. Okay, fine. Thank you. Yeah. Okay, so now I want to say something, but I already showed you some rigidity theorem. I want to sort of explain a general scheme to prove ME and Qi rigidity. So this is certainly not the only way to prove ME and Qi rigidity, but this kind of scheme was sort of responsible for a collection of results. So I think it's worth mentioning. So okay, the idea is that okay, so I take some mysterious countable group. So suppose I wanted to prove a rigidity result. So I want to say any group measure equivalent to this group or Qi to this group is more or less this group. Okay, so now how would I go? So basically, first the step is instead of consider any group which is ME or Qi to this particular group, then there's a general reduction procedure to just reduce to study the self-quasi-isometry or self-ME coupling of the group with itself. Okay, so this is like a general reduction which works for any group. Okay, and then so now the second step is I want to sort of find a collection of subgroups. I want to find a collection of subgroups which are preserved by any self-quasi-isometry or any self-ME coupling. So my preserve is a bit more subtle in the ME case. So, but in the Qi case, it just says that any self-quasi-isometry send one of the subgroup to another subgroup up to find a household distance. Okay, so this kind of thing. Okay, so now, and we also want to say this preserve the intersection pattern of these elements. And then the last step is, okay, so we want to show the intersection pattern of this collection subgroup is rigid. Okay, it's kind of the last step is combinatorial. Okay, so maybe I can even clarify a little bit more. So let's say what usually happens is that in the second step, I can usually define some kind of graph or symmetrical complex encode the intersection pattern of this collection subgroup. In the case of mapping class group, in the both QI and ME case, this subgroup to be the is going to be chosen to be the stabilizer of a curve for the mapping class group acting on the curve complex. Okay, and then so now from step 2, we actually had a homeomorphisms because every element in the QI we're going to induce automorphism of this sort of symmetrical complex. And step 3 is supposed to prove that the automorphism of this symmetrical complex or graph is somehow small. Okay, so that's sort of one particular strategy. So that's how the mapping class group result in both QI and ME side are proved. Okay. Okay, so now I want to comment on, okay, we had step 2, we said that step 1 works for all groups. Step 2, okay, so how would you choose such subgroups? Okay, so this is actually quite interesting. So now I want to impose a group with non-positive curve in some sense. So it could be Halley or cat0 or HHS or cross median. So let's say your favorite notion of non-positive curvature. Okay, and then okay, so let's say if you have a non-positive curved space, then you have some, let's say, some zero curvature like flats or quasi-flat, and you have some hyperbolic direction. And then the general philosophy in QI side is to somehow there's a contrast between flatness and the hyperbolicity, which is detected by the quasi-isometry. Okay, and then in the ME side, so it turns out that the amenability is a ME invariant, and then in the ME side is we're usually trying to explore the contrast between ME, the amenability and non-amenability. Okay, so to say it more precisely, so for example, in the QI side, we can try to show that some negative curve direction are preserved or some flats are preserved. And then in the ME direction, we're trying to show some amenable subgroup are preserved. So things like that. Okay, and then so somehow I think there's an amazing theorem by Adam and Bellman says that if you have a non-positive curvature, then amenability and the flatness is more or less the same. So they say that if H is amenable subgroup of a cat0 group, okay, this is proof by cat0 group. I don't know whether the expert can knows whether this also knows other form of non-positive curvature. Okay, so any amenable group is actually virtually abelian. So the amenability and the flatness, they coincided. So then this was the reason why I was expecting that maybe if the group is non-positive curved, then the QI invariant and the ME invariant may align. Okay, maybe they align for a different reason, but they maybe align. Okay, so and then actually we actually had some examples. So we will take the G to be the fundamental group of complex special cube complex, which is not hyperbolic. I want it to be not hyperbolic, so I can exploit the contrast between flatness and hyperbolicity. And I also want it to be not relative hyperbolic. It turns out in the ME side, if it's ME does not quite distinguish hyperbolic and relative hyperbolicity. So that's so I have to put this condition. Then somehow then the maximum product subgroup, that means subgroup which are product of infinite two infinite subgroups, and which is not contained in other products. So this will mean by maximum product subgroup, they're both QI and ME invariant. So the QI case was proved by different cases by different group of people, and the ME case is joint work with Horbez. Okay, so this is already one sort of like evidence towards this this kind of thing. Okay. Okay, so this is my comment on step 2. Okay, so to summarize, I would expect that okay, so this is I cannot make this statement more rigorously because it's like a vague statement that maybe under some form of non-positive curvature, some of the QI invariant and ME invariant would align. Okay, so okay, so now I want to also comment on step 3. Okay, so now okay, so step 3 is basically says that the intersection pattern of this subgroup, they are sort of rigid, right? Okay, so then I think it's not hard to believe that in general there's no reason why this is true. So for this is true for mapping class group that come from a highly non-trivial theorem that the automorphism of the curve complex basically come from the mapping class group. But if you take a more general cube complex or non-positive curved space, then this might fail because if, for example, if I look at this, if you already know the quasi-isometric group of the group is pretty huge, then we should not hope the automorphism group of this graph is small, right? So that means in particular, this step 3 will fail. So this whole strategy would fail if you already know the quasi-isometric group of the group is small. If you already know the QI group of G is huge. Okay. So now the natural question is, okay, so what if step 3 does not quite work? Okay, so for example, if you take a group with huge QI group, and it cannot be detected by the automorphism of some graph with small automorphism. Okay, and then okay, so that's kind of a situation I'm interested. Okay, so I want to say that here it's possible that it's still somehow rigid, but rigid maybe for a different reason. Okay, so now and today I want to talk about maybe what I believe will be one of the simplest examples where you can sort of run this strategy up to step 2, then you fail at step 3. Okay, so that's rectangle Artin group. I just want it to be as simple as possible. Okay. Okay, so now I want to do, yeah.
Where does the group G hat come in? Are you thinking if this is being equals to the automorphism group?
Perfect. So yeah, exactly. So when the automorphism group is small in some sense, for example, the automorphism is discrete or locally compact, then that would be your G hat. Okay, so this is another very good question. So this is another sort of independent question. If I give you a discrete group, is there somehow a canonical locally compact group which contains this discrete group as a lattice? Okay, so I think that's sort of related to your question, right? So it turns out this question is also related to ME and QI rigidity. If you have ME and QI rigidity, that will give you this canonical locally compact group. Okay.
Well, in your definition of rigidity, you just said there exists a G hat so that the group, you know, H goes into the G hat, but maybe there's different G hats.
Right, there could be different G hat, but they're all related by some kind of some relatively trivial operations like quotient by a compact subgroup. So in this case, it will say compact instead of finite. Okay, so it's like a trivial operations. Okay, so now I want to look at the class of group I want to study. So rectangle Artin groups. I would still make a definition, even I believe most of you knows about it. So okay, so I want to define in a more general context of graph product. I'm going to take gamma to define a simple graph, such that for each vertex I'm going to associate a group. So that's the vertex group. And then the graph product is basically I start with the free product of all the vertex groups, and then I demand the 2 vertex group to commute if these 2 vertices are adjacent. Okay. So the example you have in mind is if gamma is a complete graph, then the graph product is a direct sum of all this vertex group because they all commute with each other. And if it's discrete, then the graph product is a free product. And then so now the case we want to look at is if each vertex group is Z, then the graph product for the rectangle Artin group is defining graph gamma. So now the question I want to ask is what can we see about group ME to rectangle Artin groups? I already sort of told you before that the strategy in my previous slides does not quite work. So step 3 is going to fail. And there's actually a more explicit way to see the failure of the step 3. So okay, so first I'm going to start with this fact also I mentioned before that all amenable groups are measure equivalent to each other. So in particular, the countable amenable group to Zn are exactly a collection of amenable groups. Okay, and then it turns out this kind of phenomenon sort of propagate to any rectangle Artin group. So what we observe is that any rectangle Artin group is measure equivalent to graph product of any infinite amenable group with the same underlying graph. So that means you can replace each Z by any amenable group. Then there's still ME. So there's no hope to saying that any group ME to the reg is virtually isomorphic to the reg. Okay, so okay, so now is this the end of the story? So I tell you I want to prove a rigid result, and then it's not rigid. Okay, so this is not the end of the story. Okay, so okay, so I also want to mention that the groups which are ME to free group is very mysterious. Nobody understood that. Okay, so contrast to what happened in the QI side. Okay. So okay, so now I want to say, okay, so this is not the end of the story. We can still prove some rigid result, but we have to sort of slightly massage the definition of ME. So I think that I want to say that there is actually sort of a definition, a variation of the definition of ME, which is sort of a mixture of some MEs, ME stuff and some QI stuff. Okay, so it's going to take the word metric of the group into consideration. So this is called the LP metric equivalence. Okay, so now I want to introduce the definition. Okay, so now I'm going to start with a metric equivalence coupling of these two groups. Okay, so recall that means that I have G times H on some metric space, such that the action of each factor admit a finite metric fundamental domain, and each factor is free. Okay, so this is just to record the definition of ME coupling. Okay, so now what I'm going to do is I'm going to take X to be the fundamental domain of G. Then the measurability, the metric space, I can just think about the metric space as G times X. Okay, so there's no difference from a point of metric space. So now I'm going to draw you a picture. So now let's say I have this X and I have this G. I'm going to think the whole group, whole space omega as G times X. Very simple picture. And let's think about how H would act on this space. So we know that H, the action of H and action of G would commute. So that means H is going to send a G orbit to another G orbit, right? So that means, okay, so in this picture, the G orbit are just this vertical lines. So what H would do is actually going to permute this vertical lines, okay? So that means what will happen is that if I start with the fundamental domain, so let's say this horizontal line is my fundamental domain, which my choice X times identity, okay? And then I apply an action for H. It's going to send this fundamental domain to some graph, right? And then so now I have a graph over something, and it's the vertical direction is G. So I can try to measure how far is this graph deviate from this section I start with. Okay, so I'm going to define a map which is called cocycle. So it's dependent on two arguments, H and X. So what is, I'm going to define alpha of HX, how it's defined. So I start with X. X is a point in big X. Okay, I'm going to apply my action of some element H. So here you plug in this H, and then it's going to send X to some point in this graph. And then so the definition of alpha HX is going to take some element in G, which bring this HX back to its fundamental domain. Okay, it's sort of this whole, if you like, this sort of this vertical difference. Okay, so that's basically my definition of alpha HX. So this depends on X and depends on H. And then it basically measures the vertical difference between this point and that point. Okay. So now what I'm going to do is I'm going to sort of mix. So I should say that this is a cocycle. Essentially, the measure, all the information of measure equivalence is encoded in this cocycle. In other words, if I tell you what is the cocycle, you can somehow review the measure equivalence. Okay, so that's sort of no news of information. So sometimes it's also more common for people to think about this kind of cocycles instead of measure equivalence. Okay. So now what I'm going to do next is okay, I'm going to reserve this picture here. So and then so we say LP measure equivalence. So now I'm going to demand the G and H are finite generated. So it has a word map. It has a word metric. And then so now what I'm going to do is I require that this cocycle alpha HX is an LP metric on X for each H inside this big H. So this roughly means that the difference between this graph and the section is like an LP metric. It's a LP integrable function. Okay, so it basically says that the action of H, this graph and the action of H cannot be too wild. Okay, so respect to the word metric on G. Okay, so that's sort of the rough way to think about it. Okay, and similarly, I want to symmetrically put the same condition on the other cocycle GY. Okay, so this is the definition of LP measure equivalence. Oh yeah, there should be beta. Thank you. Yeah, so this is another cocycle. So you do things symmetrically. Okay. So maybe I pause for a while. see any questions about the definition? Okay, so the last comment I want to say is that definition is independent of the choice of word metric. And the simplest way to think about it is somehow I take this section and I apply edge, it's going to give you a graph. And it basically says that this graph cannot be too wide. Okay, so that's what it's trying to say. Okay. And another comment is that I'm going to say L1 metric equivalence is also called an integral metric equivalence. So this would be a definition which sort of somehow take the word metric of the group into consideration. Okay, so it's like saying that the coupling between these two groups somehow does not disturb the word metric of the group too much. Okay. Yeah.
So I think that equality is the strongest sometimes.
Yes. Yes. Quasi-isometry.
Does it give more versatility?
Yes. Yes. Okay. So L infinity metric equivalence actually give you a Lipschitz embedding from one group to another. Okay. So a Lipschitz embedding from one group to another. So it's the strongest one. Okay. Okay. So now, yeah. So this is the definition. So should I pause for a bit more to see whether there's questions? Okay, so then I think this is probably the hardest part of the talk is to absorb this definition. The rest will be easy for you. So hopefully. Okay, so and then the way I like to think about this is just this graph is not too wide. Okay, so okay, so now I'm going to define two finite geometric group LP ME if there's a LP metric equivalence between them, and I'm going to say L1 ME is sort of an integral ME. Okay, it's also called an integral metric equivalence. And then so now here comes the good news. So we said before that all the amenable groups are sort of metric equivalents to each other. But then it turns out, interestingly, if you add this integrability condition, then somehow it actually detects Zn. Okay, so this is a very nice result by Tim Austin that if a group, a finite geometric group is L1 ME to Zn, then H is virtually Zn. So notice that in the definition of L1 ME, I have to take finite generated because it has a reference to the word metric on both groups. Okay, so that's a different small difference from the definition of ME. We just require countable group. Okay, okay. So now this actually give this is the thing which give us hope it's actually possible to do something in right-angle Artin group. So because we said before that the problem with right-angle Artin groups, we can replace each Z by any amenable group and still stay in the same ME class. But here Austin says that you cannot do this if your group is Z. Okay, so you cannot do this. Okay, so now there's another result. So that if a group it says that if your group is L1 ME to a lattice in the isometric group of Hn, then it's virtually a lattice in the isometric group of Hn. Okay, so now let me mention that. Okay, so this statement is well known in the QI side. It's not known for ME. So if you drop this L1, nobody knows what happened. Okay, so but there is at least a L1 version. Okay, so I want to say that in general, the metric equivalence classification of hyperbolic group are extremely difficult. Okay, so there's not many invariant. Okay, so now you could also ask about free group. Okay, so would expect that if a group is L1 ME to a free group, it probably is also free. That would be the ideal situation, but that's still open. And I think Bowen proved some partial result. He says that you not only have to require L1 ME, you have to require something stronger, then you know the mysterious group is the free group. Okay, so but this question itself is open. Okay, so now I also want to say that despite we have some positive news, in general, this integral metric equivalence and the quasi-isometry, they are not the same thing. So it's a result by Shannon that for NDP, you can always find finite geometric group which are LP metric equivalence but not quasi-isometry to each other. And these examples are actually lattice in some hyperbolic space. So basically, the things that some of the lattice could be ME, some of the co-compact lattice could be LP metric equivalence to some of non-co-compact lattice. Okay. So now I think it's the time to say the main thing. So So I said that I wanted to understand. Well, okay. So you see that in ME measure equivalence, there's something related to word metric. So it's a natural question. Whether it's actually, at least for some class of group, whether it's the same as quasi-isometry. Okay. So what we prove, the main thing is that if I take a torsion-free finite geometric group, and if that group is L1 ME to a rectangle Artin group with finite automorphism group, then H is actually quasi-isometric to the rectangle Artin group. Okay, so now I want to make some comments. So here torsion free is not an ideal assumption. So we can replace torsion free by uniform bounded torsion, but we don't know what happened if I allow the torsion to grow. Okay, so this is one thing which is a bit mysterious. We do know that there actually are some non-uniform lattice which are L1 ME to product to free group. Okay, and the torsion become bigger and bigger. Okay, so this is actually rather subtle to sort of treat the case without any torsion, without the uniform bound on the torsion. Another thing is that here in this generality, we cannot hope for a rigidity result, because in general, we're going to see examples later that there are examples where H is actually not virtually isomorphic to G. Okay, so here is just the bridge between L1 ME and the quasi-isometry. And also this requirement of finite out, it sort of says that the group has some kind of rigidity statement, says the group have some kind of limited algebraic symmetry, and it can be read directly from the defining graph. So that's very simple conditions where you can do that. Okay, so now our end game is to try to prove some L1 ME rigidity result. So now so here is there's already a bridge between L1 ME and the quasi-isometry. So now I can use some existing result on the quasi-isometry to try to deduce something about metric equivalence. Okay, so this will be a way to use QI for ME. Okay, so this is one thing we proved before. Okay, so the next question you would ask is, what can you say about group quasi-isometric to rag? So this is one thing we proved a few years ago. So I take a rectangle Artin group with finite out, so we can cubulate any mysterious group which are quasi-isometric to a group with finite out. And then the cube complex we get is actually very similar to the canonical cube complex associated with the rectangle Artin group. But we have to do some small deformation. So it's not exactly a cube complex. And I'm going to show you some reason why it's impossible actually just to choose the original cube complex. Okay, so there has to be some small deformations. Okay, so now if we put this together, then we have the following corollary. So if I take a torsion free or a group which is L1 ME to a rectangle Artin group with finite out, then it's going to act geometrically on some case of cube complex, which is small deformation of the canonical cube complex associated with rag. Okay, so we have a nice geometric model to work with. And then so now the next question is, because eventually we want to get to rigidity. So now you ask, okay, so what can we say about a group acting geometrically on this cube complex? This cube complex we get. Okay, so then this is basically, this gives rise to the connection to virtual specialists. So okay, so now what we show before is that I take a rag with finite out, and I'm going to add two extra conditions, star rigid and contain no induced force cycle. So this is a condition I'm going to explain later. Then it turns out the all uniform lattice acting on all cube complex arise from this slice. They're all commensurable to the rectangle Artin group. Okay, so this tells us what are these groups. And so here induced force cycle is basically a force cycle in the defining graph without diagonal. So the force cycle means, geometrically means that the force cycle means you have a product of two trees, product of two infinite-ended trees inside the rectangle Artin group. And it turns out this condition is sharp. So whenever actually one can show that whenever I had an induced force cycle, then this statement is never true. Okay, you can always find the groups which acting on this cube complex, but they're not compensable to the rag. Okay, so this comes from and then the star rigid is a condition I wanted to drop, but for some reason I haven't managed to do that yet. So it's a technical condition. We require the automorphism of the graph is somehow small. So the precise condition is that if the automorphism graph fixes the closed star of a vertex pointwise, then the automorphism must be identity. For example, if you define a graph is a polygon, then it will work. Okay. So, or if you define a graph does not have any symmetry, then it will be star rigid. Okay. Okay, so now, so I should say that the key statement. So how is this connected virtual specialist? So a key step is to prove that the action of all these lattices are actually virtually special. And then so now there's actually, I should say there's actually later there's actually once you get virtual specialists, then you could ask what's the relation between virtual specialists and the conventionality. And I should say that very recently that's it a much more general result than what I originally proved. So it's Sam Shepard who is actually here. So he obtained result of a relation between virtual specialists and convention. That is actually a very large class of Kaiser cube complexes. Okay, so that's somehow how things are related to each other. Okay, so now if we put all this together, then we actually had a rigidity result. So I mean rigidity result. I take a random Artin group with find out. I take some graph which is star rigid and does not contain induced full cycle. If I take any torsion-free finite geometry group, which is I1, I to G, then H is virtually isomorphic to G. Okay, so this is somehow the way. If the step 3 fails, we actually somehow have to use this kind of virtually special machine to get this result. Okay, and then so again, so this kind of rigidity will fail if you whenever gamma contain induced full cycle. And I should say that, so now I wanted to comment on, so here I said that this is sort of strong rigidity holds true for some class of radical Artin group. And you could ask whether, in the case where the strong rigidity fails, whether you had the slightly weaker form of rigidity that you can have like a common locally finite, locally compact topology group where you can sort of uniformize all the group which are in the class, which are L1 ME to your rank. And it turns out that this is actually not true. Okay, so we can find a radical Artin group finite out. Actually, we'll find an infinite family of radical Artin group finite out, such that if we consider the class of group which are L1 ME to the group, then we cannot, that does not exist any local compact topological group such that any member of in this class is virtually lattice in this G hat. Okay. So now this is also, we will also explore the relation between virtually specialists. Somehow, we know that virtually specialists will obstruct conventionality. So if you have a group which is virtually special, another group is not virtually special, then they're not conventional. And here we sort of prove an even stronger result. We're going to show that they're not, the group we construct is not virtually special, but then they're not only conventional, we cannot even find any locally compact topological group to put them inside. Okay. Okay, so these are the sort of the statement of the main result. So now I think maybe I have a bit time left. So I have maybe 5 minutes left. So I'm trying to say a bit about the proof. Yeah.
You know what? Raise the proof of A2 with equivalence in the last.
So here in the last step, so we actually prove A infinity and QI. So this class they're sort of A infinity and QI. So but then they somehow still cannot be uniform by some compact model. Okay, so now I want to say a bit about proof. So I think here, because the new result here, so some of the results are old result. The new result here, the main new result is the bridge between QI and the I1ME. So I'm going to only talk about how we establish the bridge between I1ME and QI. Okay, so now the key tool we want to use is radical computing. This is actually some object where rules already defined in her talk for actually more general Artin group, but I'm just going to remind you how it works in the rectangle Artin group. Okay, so I'm going to use a rectangle, take a rectangle Artin group, and notice that each complete subgraph will give you an abelian group because it gives you generators which commutes. And then so I call this abelian group standard abelian group, and also I'm going to say that the trivial subgroup is also a standard abelian subgroup. Okay, so by definition. Okay, and we're going to define a standard flash is going to be a left coset of a standard abelian subgroup. And then, okay, so now this is enough to define the radical building. So so now I'm going to just take the collection of standard flats. So notice that since the trivial subgroup are standard abelian group, that means standard flats also contain each element in the group. Okay, so so these standard flats form a poset. Basically, we can just order them by inclusion. Okay, so this is the poset, and then so the space I'm going to use is going to be the geometric realization of this poset. So namely that the vertices are basically it's going to be a symmetrical complex. The vertices are in one-to-one correspondence in element in this poset, and the symplices are basically chain in one-to-one correspondence to chain in this poset. Okay, chain means a collection of a sequence of elements, let's say A1 less than A2 less than A3 less than A4. So this is what I mean by chain. Okay. Okay. So this turns out to be a cat0 space. Okay, so that's one of the key things we're using. So notice that the group is going to act in this space because the group is going to the left translation of the group is going to permute the standard flats, and it's going to preserve respect the inclusion. So that's why we have that group acting on this complex. Okay, and the stabilizer of cells are basically conjugate of the standard abelian subgroup. So the cell stabilizer are all abelian. Okay. Okay, so I also need a bit more terminology. So I'm going to define the rank of a vertex in the rank building. So that's going to be the rank of the abelian subgroup in the associated coset. Okay, so because each vertex corresponds to an element in this coset, and each coset is a standard flat. It's basically some coset of abelian group, and then the rank of that abelian group is going to define to be the rank of the vertex. Okay. Okay. So in particular, I always want to emphasize this in the rectangle Artin group. I will see a lot of rank 0 vertices, and they're actually one-to-one correspondent with element in the group. Okay. So now this is the space we want to work with, and then so now the first step is that So you have a rectangle Artin group find out, then I take some mysterious group with bounded torsion, which is ME to G. So notice that here is ME, not L1 ME. So now here in general, what I would know is that the group is going to act on the rectangle building cocompactly, such that for any vertex stabilizer, the H stabilizer is ME to the G stabilizer. Okay, so this is true for any ME. So this we haven't used L1 yet. So now here what we know from this, so if H is bounded torsion and H is ME to G, the H acts on B with a minimal stabilizer, because we know the stabilizer of G, the G stabilizer of the rectangle Artin group is abelian. So the H stabilizer is battery equivalence to the G stabilizer, so the H stabilizer has to be amenable. Okay, so this is what's true for general rectangle Artin group. We always acting on the rectangle building with amenable stabilizer. And then you would expect the next step I want to do is, under the assumption of L1, I want to sort of reduce the amenable stabilizer to abelian stabilizer. Okay, so that's exactly what we do. So okay, so I want to say that assume G and H are L1 ME, then I want to say that the H stabilizer, or the action of the H stabilizer is actually L1 ME to the G stabilizer. Okay, that's what I want to show. But then there's a big problem, because if you still remember, the definition of L1 ME require that both two groups are finitely generated. Otherwise, we cannot even define what is L1 ME. So now the main issue is that I don't know why are these vertex stabilizer finitely generated. If it's not finitely generated, then we cannot say it's L1 ME. We have not even defined this notion. Okay, so that's actually the main obstacle. But I think that's one good news is that okay, so in general, also I should say in general, the vertex stabilizer could be infinite generated. So there's no topological reason to force the vertex stabilizer to be finite generated. Okay, so we have to use something more. Okay, so here, so what actually happened is that if you remember in the definition of L1 ME, we have the co-cycle on two sides. I have the co-cycle, for example, H prime is ME to G, ME to Z. Then I have a co-cycle from H prime to Z, and also have a co-cycle from Z to H prime. So now here, what I know is that what I can still know is the co-cycle from H1, H prime to Z is L1 because I had a word metric on Z. So that means one direction of the definition of L1 ME still works. And that's the thing which actually enable us to show that if I so some of this group, so this vertex plate is actually finitely generated. So this is actually the key lemma. So we show that if I have a L1 I'm embedding into some abelian group, let's say Z, then I just take some countable group. Then the countable group has to be finitely generated, and actually it's virtually isomorphic Z. Okay, so this is how we handle this finite generated this of the vertex stabilizer. Okay. So now I know all the things are finite generated, then I can happily say that the all L1 ME, I can use this result by Tim Austin and say that they're actually all virtually isomorphic. So now I'm in a very good situation that I have my mysterious group actually on the same complex as the rectangle Artin group and has the virtually isomorphic stabilizers. So now you could ask, okay, so what this implies actually is virtually isomorphic G? The answer is no, so we have to do more work. Okay, so now the last step. Okay, so the last step of the proof is that so now I need to explain what is exactly going wrong with this. So okay, so now we have everything seems to be aligning up, but there's like one extra problem. So okay, so now I think about the mysterious group acting on the rectangle building. It's going to preserve the collection of rank 0 vertices. Okay, so now recall that rank 0 vertices correspond to the element in the group. So we actually has a mysterious group H acting on the rank G gamma, and the action is free and co-compact. And by definition, it's going to send standard flats to standard flats. I'm going to call this flat preserving action. Okay, so this is what structure we can extract from the previous slides. And then so now the problem is that these flat preserving bijections that they're in general very bad. So they're far away from being an isometry. Okay, so here's an example. So let's say we're just in a free group. Let's say generated by A and B. So I have the vertical lines are, let's say A lines are horizontal lines are B lines. And I could have a bijection which send A lines to the A line, B lines to the B line, but I can just swap these two levels. Okay, so this is actually the problem that we would have a lot of these permutations, which sort of does not respect the order are known a standard line. Okay, so now since I'm running out of time, so maybe I'm going to say things very simply what happened in the next. So you see the problem is that the action does not have to respect the order unknown at 9, right? And then you could have arbitrarily complicated permutation group which mess up the order. And then so now so I'm going to finish very quickly. So here the key point is that if you know that your order is somehow quasi-preserved, then you know the action is actually conjugated to an action by LA actions. Okay, so basically there's a small lemma about says that if we have this mysterious action, okay, if you know that it considered action on the standard line, if the action somehow quasi-preserve the order, that means it's conjugated to an action by quasi-matrix, then the whole action is kind of conjugate to an action by quasi-matrix. Then you can deduce the group is quasi-matrix G gamma. And the most magic thing is that it turns out under this metric equivalence coupling, we can actually show that these actions on these lines, they're not too bad. So we don't have like a crazy symmetrical group, symmetry group acting. So somehow we can show the regularity of these actions, which sort of rule out some crazy action on this line, and that we indicate the quasi-symmetry. Okay, I think I'm done. And sorry for running over a little bit. Thank you very much.
Now there's time for one quick question.
We had a result earlier on about impact of the complex, and then another group that was quasi-isometric acting on a distorted version of that theoretic complex. Is that right?
Right. Okay, so you're wondering what is the cube complex? Or what is the distorted version of the cube complex? Is that your question? So okay, so the distorted cube complex come from the permutations. Because of the permutations, so we have to, so in here, I cannot act on 9 anymore. Then I have to sort of, if I permute these 2 points, I have to sort of glue this. Okay, maybe I think the best thing is I'm going to draw you some picture because it's going to take a bit time to explain. Okay, sorry. Yeah.
That's what's playing between the end.